Welcome to this coding problem walkthrough. Today, we'll be exploring problem number 514, Freedom Trail. We'll break down the problem, discuss different approaches, and guide you step by step through solving it. Let's dive in. In this problem, we are working with a circular dial that contains all the lowercase English letters arranged in a circle. The objective is to figure out the minimum number of steps required to spell a given target string, called the key, by rotating the dial and pressing the center button. The circular nature of the dial means that you can rotate either clockwise or counterclockwise, and each single step of rotation counts as one step. Pressing the center button to select a character also counts as one step. The starting position of the dial is such that the first character of the string ring is aligned at the 12 o'clock position. The challenge is to navigate this circular dial efficiently to spell out the target string while minimizing the total number of steps required. The solution to this problem involves calculating the total steps needed to align the desired characters of the target string. For example, consider the input ring as Gotting and the key as GD. Initially, the dial starts with the letter G at the 12 o'clock position. Since the first character of the key is also G, no rotation is needed, and you can simply press the center button to select it. This action takes one step. Next, you need to align the second character of the key, which is D. To align the D, you would rotate the dial one step clockwise, which takes one step, bringing D to the 12 o'clock position. Then, pressing the center button to select D adds another step. In total, you need one step for selecting G, one step for rotating to D, and one step for pressing the button to select D, making the total number of steps 4. Another example illustrates this further. If ring is ABCDE and key is odd A, you start with A at the 12 o'clock position. Selecting A takes one step, since no rotation is required. After selecting A, you need to align the next character in the key, which is D. To do this, you rotate the dial 3 steps clockwise, which takes 3 steps, and then press the center button to select D, adding another step. Finally, you align the last character in the key, which is E, by rotating one step counterclockwise, taking one step, and pressing the center button to select it, which adds another step. The total number of steps here is 1 for selecting A, 3 for rotating to D, 1 for pressing D, 1 for rotating to E, and 1 for pressing E, resulting in 8 steps overall. In a final example, if ring is ABCDF and key is FDA, you start with A at the 12 o'clock position. To select F, you rotate one step counterclockwise, which takes one step, and then press the center button to select F, adding another step. Next, to align D, you rotate 2 steps counterclockwise, taking 2 steps, and press the center button to select D, adding one more step. Finally, to align A, you rotate 3 steps clockwise, taking 3 steps, and then press the center button to select A, adding another step. The total number of steps is 1 for rotating to F, 1 for pressing F, 2 for rotating to D, 1 for pressing D, 3 for rotating to A, and 1 for pressing A, which makes a total of 10 steps. With these examples, we also need to consider edge cases, such as when ring and key are single characters, when they are identical, or when the key contains repeating characters. These scenarios help ensure our understanding of the problem is robust and complete. To begin solving the Freedom Trail problem, the first approach we might consider is a brute force or exhaustive search. Here, the idea is straightforward. For every character in the target string, we iterate through the dial and calculate the cost of moving to every possible occurrence of that character from the current position. Since the dial is circular, we leverage the fact that moving left or right can sometimes achieve the same result, and the movement cost is calculated as the minimum of the direct distance and the wraparound distance. While this approach ensures we explore all possible paths to spell the target string, it's computationally expensive. Specifically, the time complexity grows exponentially as it explores all combinations of movements, making it impractical for larger inputs. Additionally, the recursion stack consumes extra memory proportional to the length of the target string. Although this method is conceptually simple, the sheer inefficiency for larger constraints makes it unsuitable for realistic scenarios. Now, to overcome the inefficiencies of the brute force method, we turn to a more optimized approach using dynamic programming with memoization. The key insight here is to avoid recalculating the cost for overlapping subproblems. Instead, we break the problem into smaller states and build the solution incrementally. Specifically, we focus on minimizing the number of steps required to spell the target string by considering all possible positions in the ring for each character. The state can be represented as dp, I, j, where I denotes the index of the target string, and j is the current position in the ring. This state tracks the minimal cost to spell the target string up to index I with the ring pointer at position j. To compute this, we iterate over all occurrences of the current target character, calculate the cost of moving there from the previous character's positions, add the pressing cost of selecting the character, and store the minimum result. By pre-processing the ring into a dictionary of character indices, we can quickly access all relevant positions during computation. Using recursion with memoization, we ensure that each state is calculated only once, significantly improving efficiency. The dynamic programming approach, with its use of memoization, offers a significant improvement in both time and space complexity. The time complexity is reduced to O, n asterisk k, where n is the length of the ring and k is the length of the target, while the space complexity is also O, n asterisk k, primarily due to the memoization table. This efficiency makes it scalable for larger inputs. By storing intermediate results and reusing them, the method avoids redundant calculations, which is the main drawback of the brute force approach. Additionally, the pre-processing step that maps each character to its indices in the ring enables faster transitions between states. While this method does require extra memory for the memoization table, this trade-off is justified by the significant reduction in runtime. The dynamic programming approach strikes an excellent balance between simplicity and efficiency, making it the optimal choice for solving the freedom trail problem. Its ability to effectively handle both time and space concerns ensures that it performs well even under larger constraints. To solve this problem, we need to understand the mechanics of the circular dial and how we can spell out the target string with minimal steps. The dial is represented as a circular array of characters, such as a B, C, Z. To move from one character to another, we can rotate the dial either clockwise or counterclockwise. This introduces the concept of distance, which is the minimum number of steps required to move between two positions on the dial. The clockwise distance is the absolute difference between their indices, while the counterclockwise distance is the total length of the dial minus the clockwise distance. Additionally, we can map each character to its indices on the dial using a dictionary. For example, A might appear at positions 0 and 26 if the dial wraps around. This mapping allows us to quickly look up where each character occurs, which is essential for minimizing the steps required to spell the target string. With the character indices mapped, we can now use dynamic programming to determine the minimal steps needed to spell the target string. We define a DP table, where DP, I, J, represents the minimum steps required to spell the first I characters of the target string, with the dial ending at position J. The transition formula calculates the minimum cost of reaching J from all possible previous positions K for the current character in the target string. This is done by adding the distance between K and J to the value of DP, I1, K. The base case initializes DP, 0, J, to the distance from the starting position to all possible positions of the first character in the target string. Finally, the solution is found by taking the minimum value in the last row of the DP table, which represents the minimal steps required to spell the entire target string. To optimize the space complexity of our dynamic programming approach, we can use a rolling DP array. Instead of maintaining the entire DP table, we only store the current and previous rows, which is sufficient to compute the transition states. This reduces the space complexity from O, n asterisk m, to O, m, where n is the length of the target string and m is the number of characters in the dial. The algorithm's key insights include leveraging the circular nature of the dial to compute the minimum distance efficiently, accounting for multiple occurrences of characters on the dial, and utilizing dynamic programming to systematically explore all possible paths while avoiding redundant computations. The two primary data structures used are the dictionary for fast character index lookups and the DP table for tracking minimal steps. This combination allows the algorithm to strike a balance between time and space efficiency. The time complexity of the solution is O, n asterisk m, where n represents the length of the target string and m represents the number of characters in the dial. This arises because, for each character in the target string, we must evaluate all possible positions on the dial. The space complexity is reduced to O, m, by storing only two rows of the DP table at any given time. When implementing this algorithm, we must also address certain edge cases. For example, targets with a single character should still compute the minimal steps correctly. Repeated characters in the target string must be handled efficiently to avoid redundant calculations. For dials with a large number of characters, the algorithm should scale appropriately, and when distances wrap around the end of the dial, the computation should correctly account for the circular structure. These considerations ensure that the algorithm is both robust and efficient. To illustrate the algorithm, consider the example where the dial has characters of B, C, D, E, and the target string is ACE. First, we pre-compute the character indices, mapping each character to its positions on the dial. For instance, A maps to position 0, C to position 2, and so on. We then initialize the base case of the DP table by calculating the distance from the starting position to the positions of the first target character. Using the transition formula, we iteratively compute the minimal steps for each subsequent character in the target string. Once all characters are processed, the final answer is the minimum value in the last row of the DP table. For this example, the minimal steps required to spell ACE is 6, demonstrating the effectiveness of the algorithm in minimizing the dial's rotations. Here, we begin by importing the necessary libraries, specifically the defaultIC from the collections module, which will help us efficiently map each character in the ring to its indices. We then define a class called solution and implement the method findRotateSteps. The inputs to this method are the ring, which represents the circular sequence of characters, and the key, which is the sequence we need to spell out. First, we determine the lengths of the ring and the key, storing them in variables n and m, respectively. Next, we set up a defaultIC named char_to_indices. This will store each character in the ring as a key and map it to a list of indices where it appears. By iterating through the ring with a for loop, we populate this mapping efficiently. To optimize our solution, we use dynamic programming with memoization. A dictionary named DP is initialized to cache the results of overlapping subproblems. We then define a helper function, DFS, which will perform a depth-first search to calculate the minimum steps required to align the ring and spell out the key. The function takes two parameters, the current position of the ring, ring_POS, and the index of the character in the key we are trying to match, key_index. If we've matched all the characters in the key, indicated by key_index being equal to m, the base case is triggered, and we return 0. Additionally, if the current state is already in our DP cache, we return the cached result, avoiding redundant computations. The target character in the key is identified by accessing key_index, and we initialize a variable called result to infinity as we aim to minimize the number of rotations. Now, we iterate through all the positions of this target character in the ring, which are stored in char_to_indices, target_char. For each position, we calculate the distance to reach it in the clockwise direction using the absolute difference between the target position and the current ring position. Next, we calculate the counterclockwise distance by subtracting the clockwise distance from the total number of positions in the ring, n. The minimum rotation required to reach the target character is then determined by taking the smaller of the clockwise and counterclockwise distances. To account for the step involved in pressing the button to select the character, we add 1 to this rotation. We then make a recursive call to the DFS function, updating the ring position to the current target position and incrementing the key index to move to the next character in the sequence. The result for this path is updated to the minimum of its current value and the total steps calculated for this recursive branch. After iterating through all positions of the target character, we store the computed minimum result for the current state in the DP dictionary to reuse later if needed. Finally, we return the memoized result for this state. At the end of the process, the function DFS is initially called with the starting ring position set to 0 and the key index set to 0, indicating that we start at the first character of the ring and the first character of the key. The solution is returned as the result of this initial DFS call, representing the minimum steps required to spell out the entire key using the given ring. Here, we start by defining the findRotateSteps method, which takes two inputs, ring and key. The ring represents the circular dial, while key is the sequence we need to spell out. First, we calculate the lengths of the ring and key and store them in n and m. Then, we pre-compute the positions of each character in the ring using a hash map. This map, char to indices, associates each character with a list of indices where it appears in the ring, allowing us quick access to these positions during our calculations. Next, we define a memo map for memoization, which will store intermediate results to avoid redundant computations and optimize performance. Finally, we initiate the process with a call to the DFS method, starting at position 0 of the ring and the first character of the key. The DFS function will handle the recursive exploration of all possible paths. The DFS method begins by checking if we've matched all the characters in the key. If so, the function returns 0, as no further steps are required. To optimize further, we use a memo key based on the current ring pos and key index to check if the result for this state is already cached in the memo map. If it is, we return the cached result immediately. Next, we retrieve the target character from the key and initialize the result variable to store the minimum steps required. For each position of the target character in char to indices, we calculate both clockwise and counterclockwise distances, determining the minimum rotation needed. Then, we recursively call DFS for the next character in the key, adding the minimum rotation and one step for selecting the character. The result is updated with the smallest value across all possible positions. Finally, we store the computed result in the memo map and return it. This ensures our solution remains efficient, even for larger inputs. To begin solving this problem, we start by initializing some key values. The length of the ring is 7, and the length of the key is 2. We also pre-compute a map called char _to _indices, which stores the indices of each character in the ring. For example, the character G appears at positions 0 and 6, while D appears at positions 2 and 3, and so on. Next, we prepare an empty dynamic programming dictionary to store results of subproblems. Starting the recursion at ring position 0 and key index 0, we look at the first character in the key, which is G. The possible target positions for G are 0 and 6. For each target, we calculate the clockwise and counterclockwise distances. For position 0, the minimum rotation is 0, while for position 6, the minimum rotation is 1. The recursive calls then proceed with these target positions and the next key index, building the result as the minimum steps required to match the key from these positions. Now, in the next recursive call, the current ring position remains 0, and the key index advances to 1. The target character in the key is now D, which appears at positions 2 and 3 in the ring. For position 2, the minimum rotation is 2, and for position 3, the minimum rotation is 3. From here, we make further recursive calls to evaluate the cost of matching the rest of the key starting from these positions. At the base case, when the key index equals the length of the key, meaning all characters are matched, we return 0. This indicates that no more rotations are needed. Combining these results, we compute the minimum steps required to match the key at this stage. After all recursive calls are completed, we backtrack through the results to compute the final answer. This involves summing up the minimum rotations and steps calculated at each stage of recursion. For this example, the minimum number of steps required to spell the key GD from the given ring is 4. Moving on to a second example, consider the ring ABCD and the key Ace. The length of the ring is 5, and the length of the key is 3. We pre-compute the char _to _indices map again, which now maps each character in the ring to its respective position. For instance, A is at position 0, C is at position 2, and E is at position 4. With the DP dictionary ready, we proceed with the recursive solution. The first recursive call starts from ring position 0 and key index 0. The target character in the key is A, which is found at position 0 in the ring. The clockwise and counterclockwise distances are both 0, so the minimum rotation is 0. We then move to the next key character by making a recursive call to DFS 0, 1. For the second character in the key, C, we calculate the distances to its position, which is 2. The clockwise distance is 2, and the counterclockwise distance is 3, so the minimum rotation is 2. A recursive call is made to continue matching the rest of the key, starting from position 2. Now, at ring position 2 and key index 2, the target character is E, located at position 4 in the ring. For this position, the clockwise distance is 2, and the counterclockwise distance is 3. The minimum rotation is therefore 2. A recursive call is made to DFS 4, 3 to handle the next state. When the key index equals the length of the key, we reach the base case, returning 0 as no further rotations are needed. Backtracking from these recursive calls, we sum the rotations and steps calculated at each step to find the total minimum steps. For this example, the final result is 6 steps to spell the key ace. In the third example, the ring is PQRSTUV, and the key is TUV. The ring has a length of 7, and the key has a length of 3. We begin by pre-computing the char_to_ indices map, which associates each character in the ring to its respective position. For instance, T is at position 4, U is at position 5, and V is at position 6. With an empty DP dictionary prepared, we start the recursive process. The first call begins at ring position 0 and key index 0. The target character is T, which is at position 4. The clockwise distance is 4, and the counterclockwise distance is 3, so the minimum rotation is 3. We then proceed to match the next character, making a recursive call to DFS 4, 1. At ring position 4 and key index 1, the current target character is U, located at position 5. The clockwise distance is 1, and the counterclockwise distance is 6. The minimum rotation is 1. We then advance to the final character in the key by making a recursive call to DFS 5, 2. At ring position 5 and key index 2, the target character is V, which is located at position 6. The clockwise distance to this position is 1, and the counterclockwise distance is 6 as well. The minimum rotation is therefore 1. Once the final character is matched, we reach the base case where the key index equals the length of the key, and we return 0. Finally, by backtracking through the recursive calls, we compute the total minimum steps required to match the entire key. Adding up the rotations and steps from each stage, the final result for this example is 6 steps to spell the key TUV from the given ring. This concludes the detailed walkthrough of solving this problem using dynamic programming and recursion, demonstrating how we optimize the process to minimize rotations while spelling the key from the ring. The time complexity of the find rotate steps algorithm is determined by 2 main components. First, we analyze the process of pre-computing the indices of characters in the ring. This operation involves iterating through the ring of length n and appending the index of each character to a dictionary. Since each dictionary insertion is an O(1) operation, this step takes O(n) in total. Next, we consider the recursive depth-first search (DFS) with memoization. Here, the function DFS ring_POS key_index examines all valid positions in the ring for each character in the key. If the key has a length of m, and for each character in key we evaluate k positions in the ring where the character appears, then the function computes distances in O(1) and makes recursive calls for the next character. These recursive evaluations form the basis of the time complexity and are analyzed further in the following steps. To quantify the recursive evaluations, we observe that the total number of states in the dynamic programming table is O(n*m). This is because ring_POS can take n distinct values, and key_index can take m distinct values. Each state in this table is computed only once, and the work per state is proportional to k, the average number of positions for a character in the ring. Since the sum of k for all unique characters in the ring equals n, the total work across all states is O(n*m). Adding the O(n) time for pre-computing indices, the overall time complexity becomes O(n plus n*m), which simplifies to O(n*m). For space complexity, the char_to_ indices dictionary used in pre-computing indices requires O(n) space, as it stores the positions of each character in the ring. The memoization table, which stores results for all states, ring_POS key_index, also requires O(n*m) space. Lastly, the recursive call stack has a depth of at most m, consuming O(m) additional space. By combining all components, the total space complexity is O(n plus n*m plus m, which simplifies to O(n*m). Comparing this to the brute force approach highlights the efficiency of the optimized solution. A naive brute force solution would recursively try all possible alignments for every character in the key. If there are k positions for each character in the ring, this leads to an exponential time complexity of O(k) to the power of m, which is computationally impractical for large inputs. In contrast, the dynamic programming approach with memoization avoids redundant computations by caching results for each state, ring_POS, key_index. This brings the time complexity down to O n asterisk m, a polynomial time complexity that is manageable even for large values of n and m. This scalability makes the optimized solution much more effective for handling larger input sizes. Now, let's analyze the best, average, and worst cases for this algorithm. In the best case scenario, all characters in the key appear at the same position in the ring. Each recursive call involves O(1) work, resulting in a total time complexity of O(m). In the average case, the characters in the key are distributed across the ring with an average of k positions per character. Here, the time complexity is O(n*m). For the worst case, if every character in the key appears at all n positions in the ring, the time complexity still remains O(n*m) due to the constraints on the number of states in the dynamic programming table. To mathematically prove the big O complexity, we know there are O(n*m) states in total, and the work per state involves iterating over k positions, where the sum of all k is equal to n. This confirms the total work is proportional to O(n*m). On the space front, the memoization table and dictionary scale is O(n*m) and O(n), respectively, leading to an overall space complexity of O(n*m). When tackling problems like Freedom Trail, there are several common mistakes to watch out for. First, not accounting for the wraparound behavior on the dial can lead to incorrect calculations, especially when moving between characters like Z and A on a circular structure. To handle this, modular arithmetic is crucial, as it ensures you calculate distances correctly in a circular context. Next, relying on a brute force implementation can be highly inefficient. If you're recalculating the same subproblems repeatedly, the time complexity can balloon to exponential levels. Instead, you should aim to use techniques like dynamic programming to avoid redundant computations. Additionally, edge cases are often overlooked. For instance, what happens if the target string is empty, or consists of just one character? Or if the dial itself only has a single character? These scenarios can lead to runtime errors or incorrect results if not handled properly. Another issue arises with repeated characters in the target string. If you fail to reuse pre-computed results for similar states, your solution can become unnecessarily slow. Finally, overcomplicating your approach is a common pitfall. Sometimes, a simpler greedy or dynamic programming solution is more than enough to solve the problem efficiently, so resist the temptation to over-engineer when a straightforward approach works just as well. Now, let's consider some key insights that can help you stand out during interviews. Modular arithmetic is a critical concept when dealing with circular structures like the dial in Freedom Trail. It allows you to compute distances efficiently, so be prepared to explain how and why you're using the modulo operator in your solution. Another important tip is to clarify constraints up front. Asking questions about the dial's maximum size or the character set can prevent misinterpretations that might derail your approach. As you discuss your solution, think aloud and explain how you plan to optimize the brute force approach. Highlight strategies like dynamic programming, memoization, or greedy algorithms if they're applicable to the problem. Remember, interviewers value clarity over complexity. A clean, simple solution that works within the given constraints is often more impressive than an overly intricate one. On a related note, Freedom Trail shares concepts with other problems. For example, LeetCode 1048, longest string chain, emphasizes dynamic programming with string transformations. LeetCode 1216, valid palindrome 3, focuses on optimizing substring problems. And LeetCode 91, decode ways, demonstrates how to tackle recursive problems with dynamic programming. Familiarity with these can help you recognize patterns and apply similar techniques effectively. Finally, let's explore alternative approaches and their trade-offs. A greedy approach can sometimes be sufficient for specific variations of these problems. It's faster and simpler to implement but may not handle all edge cases correctly. On the other hand, dynamic programming is ideal for scenarios where you need to find minimal steps or optimal paths. However, it comes with its own challenges, such as increased space usage and the need for careful state management. Pre-computation is another strategy to consider, especially if the dial or target string is reused multiple times. By pre-computing distances and storing them in a lookup table, you can significantly reduce computation time for repeated queries. The trade-off here is that pre-computation increases space complexity. Lastly, backtracking with memoization offers a flexible way to explore all possible paths while avoiding redundant calculations. However, for larger inputs, this approach might still fall short in performance compared to pure dynamic programming. Each of these methods has its strengths and weaknesses, so the right choice depends on the specific problem constraints and requirements. Great job on making it to the end of this walkthrough. We covered dynamic programming and how to optimize the problem using caching. Remember to practice these techniques to strengthen your problem-solving skills. Thanks for watching, and I'll see you in the next one. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!